Hello and welcome to this presentation on minimum regret contracts for principal-expert problems. My name is Kasper Osterheld and this is joint work with my PhD advisor, Vince Kornitzer. I'll first give some motivation, some example of the kind of setup that we're considering in this paper. So we imagine that there's some agent whom we'll call the principal. In this case, her name is Alice, and Alice wants to make some decision. In this case, she wants to choose a business strategy for her startup. And then there's some external expert, in this case, Bob. And Bob has some expertise that is relevant to Alice's choice. But to really help Alice, Bob has to do some research. And he has various different kinds of projects that he could engage in. But all of these are costly and they vary in their costs. But he doesn't really want to do these projects just out of curiosity. Rather, he wants to make some money. And so Alice really wants Bob to acquire useful information. But to do so, she has to set some kind of incentive. So she has to set up some payment scheme that incentivizes Bob to acquire to acquire one of the available pieces of information to engage in some kind of research. And we'll also assume that Alice doesn't really know what kind of research Bob could do and how costly these different projects would be. Here's an example of something that Alice could do. A very simple contract that she could use. She could just go to Bob and say, "Here, Bob, you can have 5% of my startup." Now, Bob gets these 5% in the startup, and now suddenly he has a stake in the startup, and he really wants the startup to do well because then his shares are more valuable and he becomes more wealthy. So now Bob should really do some kind of research to help Alice. But of course, 5% in the startup, that might not be very much. So he might look at some existing data sets to form some opinion about what Alice should do with her startup. So he does some kind of research, and then he goes to Alice and says, "Yeah, I've done some research, and here's what I now believe to be best for you." Now Alice gets this information and implements the business strategy that Bob recommends. Alice could also give Bob a larger share in the startup. So she could give him, for example, 30% in the startup. And now Bob's stake in the startup is much bigger. And now he's probably much more willing to expend costs to help Alice with her startup. So now he might be willing to approach or to do some much more ambitious research project to be much more helpful for Alice. So he does so, and again he goes to Alice and says, "Well, here I've done some research, and I now believe this strategy is best." And now, because Bob gets more money, he's more invested in the project, and so his advice is probably higher quality because the information that he's willing to pay for is higher quality. The problem, of course, is that now Alice gives Bob a much higher share of the startup. And so even though Alice gets higher quality advice, she also pays or gives up a larger share of her startup. So even if her startup now does significantly better, Alice herself might end up worse off than with a smaller amount than if she just gave 5% because she has a smaller share in her startup left. We now describe the setup more formally. So there is a principal, and she has to choose between some set of possible actions. And once she chooses an action, this gives rise to some outcome from some set. And over these outcomes, the principal has some preferences represented by some utility function, and she wants to maximize the expectation of that utility function. And then there are experts, And in this paper, we not only consider the case of a single expert, although that's an important special case. We also imagine that there could be more than one expert, and each expert has access to some set of evidence variables. So those were the research projects that the expert can acquire. In this earlier example, we had Bob, who can look at, for example, some existing data sets and think about what those imply for the principal's choice. So each expert has some set of possible evidence variables that he could acquire. And associated with these evidence variables is some cost function. So acquiring some piece of evidence is associated with the cost. For example, Bob would have to spend time looking at data or do actual experiments or some surveys of consumers or something like that to advise Alice on her startup. And then the experts also have an understanding of what the evidence implies. So for each possible vector of every evidence variables, there are possible values for these evidence variables. And for each of these values, the experts know how to update their probability distribution for different actions on this evidence. So for example, if Bob figures out, okay, I learned that the demand for this particular project is low, then Bob knows how to update based on that about different business strategies that Alice might take. And then they also have these prior probability distributions over the values that different evidence variables might have. Okay, now we describe I describe the kind of mechanisms that we consider in this paper. So the expert can first choose an evidence variable that they want to acquire. Then they observe the value of that evidence variable. Of course, they have to pay the cost for that. After observing the value, they can submit a report. And this report could be the true value of that evidence variable, the true value that they observed, but they can also misrepresent this value. So, for example, they could claim that they obtained some really useful bit of information, even though they didn't. And now, of course, all of the experts simultaneously make this choice. So there's some sort of aggregate evidence, and this is then translated into an aggregated report to the principal. So the principal now sees the optimal action given the evidence that was reported by the experts. So that's E prime. That's the optimal action given the evidence E prime. And the principal also gets this distribution, which is the prediction about A E prime conditional on the reported evidence E prime. Then the principal takes the recommended action and observes some outcomes. So for example, if based on the evidence that the expert submits, the optimal business strategy is to develop some database software, then that's what the principal will do and observe some outcomes, so how well the firm does, for example. And then based on those, a score or a payoff for the expert is determined according to some function S. And this function basically is the only parameter in this mechanism. And this paper and this talk is about how to best choose this function. For example, earlier, the example of this function that we saw was just a function that looks at how much value was obtained by the principal, like how valuable the startup was, and then gives 5% or 30% of that to the expert. Okay, now the payoff to the principal is the utility of the outcome obtained minus the payoff that they have to give to the experts. So, for example, if they give 30% of the company to the experts, then they can't keep that money for themselves, of course. And the experts' utility is the score that they receive. So, for example, the share in the startup they get, minus the cost that they had to pay for the evidence that they obtained. Okay, we have to clarify a few more things about this setup. So again, our goal is to design good scoring rules or good contracts for this setting, a good functions S. And there's this sort of obvious hack that we could choose a function that is always very negative. So that would correspond to the principal just taking away money from the experts. And that's, of course, not very realistic. The experts would just never, would just stay away from this principle. And it's not very useful, not very realistic. So we have to exclude this possibility. We do this by requiring a form of ex ante individual rationality. Here in particular, it's a relatively weak form. We require that if the experts simply report their prior information and recommend the action that is best according to their prior beliefs, then their expected score is at least 0. So this prevents these kind of hacky, pointless contracts where the principal just steals money essentially from the experts. Then a more technical requirement is that we require the utility function to be normalized such that if the experts report just the prior information, then the expected utility is 0. So this essentially, the substantive requirement of this is that the principal has to know how well she can do if the experts don't acquire any information. Okay. Now, one issue is that if there are more than 2 experts, or if there are at least 2 experts, rather, then the experts together play some strategic game where each expert has to choose which evidence to obtain and what report to submit. And in general, what evidence you should obtain depends, of course, on what evidence the other experts obtain. So to address this, we will assume that the experts play a Nash equilibrium of this game induced by the scoring rule of the contract. And in particular, we will generally assume that they play the Nash equilibrium that is best for the principal. And this is related to the notion of the price of stability as opposed to the price of anarchy that is perhaps better known. And so this seems somewhat optimistic. And there are 2 justifications for this. One is sort of a very mundane and pragmatic one. The issue is that we can't really do anything to ensure that there are no bad Nash equilibria. So you can imagine cases where 2 experts both can obtain some piece of evidence, and if both obtain that evidence, then it's very valuable. But if neither of them obtain that evidence, then if only one of them obtains that evidence, then it's useless. And then it's an equilibrium for neither of them to obtain this evidence, and there's not really anything we can do to prevent such a very bad Nash equilibria. So that's one reason. Another thing that to motivate looking at the best Nash equilibria for the principal is that, well, optimize or helping the principal is the job of the experts. The experts are approached by the principal to help her make a decision. And so it is sort of reasonable to assume that the first thing they would do is sort of think about how they can best help the principal. Of course, within what is compatible with their incentives, but still, it's plausible that that's how they would think about what to do. Okay. In this paper, we're interested in linear scoring rules, or we also call them linear contracts. And these are just, I guess, the simplest kinds of contracts that you can can come up with basically. So here, for each expert, there's some value between 0 or some fraction between 0 and 1, and the expert simply is paid that fraction of the utility that is eventually obtained by the principal. So we saw this earlier in this example, that Alice just gives Bob 5% of her startup or 30% of their startup, so their alpha would be 5% or 30%. And one thing to note about these linear scoring rules is that if the experts obtain evidence E, then it is a Nash equilibrium for everyone to also report that the evidence in fact obtained honestly. So if we want to say something positive about the utility obtained in the best equilibrium by the principal, if a linear scoring rule is used, then it is enough to consider only it is enough to imagine that they report honestly, and we only really have to think about what evidence variables the experts acquire. Now we come to the question of what the goal of the paper is. So again, the goal is to design scoring rules, and specifically, we imagine, I mentioned this before, that the principal knows very little about what kind of evidence variables the experts have access to. So, for example, Alice knows that Bob is kind of an expert in business strategy, but she doesn't really know what kind of data Bob might look into, what kind of experiments Bob might conduct, how helpful that is, how costly that is. Alice wants to choose a scoring rule that does well without having to, without knowing what the available evidence is. Now, of course, if a scoring rule is supposed to always be good, then we have this problem that there are always configurations of available evidence where the expected utility is just always 0, because, for example, all evidence that the experts could acquire is very expensive, and then the optimal utility that one could obtain with any scoring rule is 0. So what we will do is we look at what's called regret. So we will compare how much the principal gets by using a scoring rule versus how much they would get if they were able to basically completely control what the experts do and if they knew everything that the experts know. Okay, let's make this more formal. So first, for any variable of for every vector of evidence that the experts can acquire, we can define the value of that information. And that is just the expected utility that the principal makes, the principal achieves, if that evidence is obtained and honestly reported. And this doesn't take costs into account yet. Then the first best solution, the so-called first best solution, is the solution where the difference between the costs, where the difference between the value of the information minus the cost of the information is maximized. And I think the best way to think about this is really imagine that that these experts were fully transparent and said upfront exactly what information they had evidence they had access to, and the principal can just tell them what evidence to acquire and only has to compensate them exactly for their costs. Then the expected utility that the principal would obtain is exactly this first best solution. Of course, the first best solution is not achievable if the principal doesn't in fact control the experts and have access to all the information that they have access to. But we will use this as a benchmark. And we'll use E star to denote the evidence variable that maximizes this term. Okay. Now we can define the regret. So the regret of using a scoring rule rather than being able to do this first best solution thing is just the difference between the first best solution and the expected utility that is obtained with the scoring rule. And again, we here imagine that, so this is the expected utility that the principal gets with the scoring rule in the Nash equilibrium that is best for the principal. So that is the regret. Okay, so we're now done finally with setup and definitions, and we can get to some of the results that we give in the paper. And I'll first give these results for the single expert case and then for the multiple expert case. The first result is a positive result on what bound on the regret linear contracts achieve. Okay, so a linear contract, again, remember, it's just the principal just gives the expert some fraction of her starter or of her utility. Then what we can show is that, so now remember that, in the single expert case, we don't have to think about Nash equilibria and so on. We can just immediately, for any given configuration, there's just one piece of evidence that or perhaps some set of evidence that the expert is indifferent between. But we can show that for all of these optimal pieces of evidence for the expert to acquire, the regret is at most the maximum of alpha and 1 minus alpha times the value of the information that is obtained in the first best solution. And to make this bound as tight as possible, we can let alpha be 1/2. So in this, that would mean that the principal just gives half of the project to the expert, and then the regret is at most the value of information in the first best solution divided by 2. Okay, that was a positive result, though the regret bound isn't particularly good, but it's a positive result. Now we get to a negative result, which essentially shows that there's no scoring rule that does any better than this linear scoring rule. And the linear scoring rule is also, with some caveat, the only scoring rule that achieves this regret bound. Okay, so let's work through this. So let's say there's any single expert scoring rule. And let's say that this satisfies the regret bound that we achieved for the linear scoring rule that just gives the expert half of the utility. So let's say that it satisfies this regret bound that we saw on the last slide in the single expert case of theorem 1. Then this scoring rule, to achieve this regret bound, it has to be the linear scoring rule that just gives the expert half of the utility obtained. And there's one small caveat to this. It can do something slightly more complicated. So this scoring rule throws away the prediction, and this theorem says that you kind of have to do so because you use a linear scoring rule. But there's one thing that you can do with the prediction. So if the expert predicts that a particular outcome never occurs, and then in the end it does occur, then you can do something else. You can, for example, punish the expert, and then you can still achieve this regret bound. But again, the main takeaway from this would be that this linear scoring rule is the only one that achieves the optimal regret bound, and there's nothing that achieves a better regret bound than the linear scoring rule. Okay, so now let's turn to the multi-expert case. So again, we imagine that we have some linear scoring rule with parameters alpha. For each expert, a fraction of the utility that they get. And again, we have a bound on the regret, and it's again some factor times the value of the evidence obtained in the first best solution. And here, this term is a bit more complicated, but again, we can choose we can choose a parameter to optimize this bound. And the tightest bound we get is if we simply set each of these fractions to 1 over n plus 1, where n is the number of experts. And then this achieves a regret bound of n times the value in the first best solution divided by n plus 1. And again, there's also for the multi-expert case, there's the corresponding negative result. So here too, if we have any scoring rule that satisfies this regret bound, which we saw on the last slide for the that we saw on the last slide was satisfied by the linear scoring rule, then this scoring rule must be the linear scoring rule, with the exception that they can score non-linearly when the expert promises that some outcome won't occur, but then it occurs in fact. Then you can score differently, but generally you have to do this simple linear scoring. And again, in particular, there's no scoring rule that achieves a lower regret bounds than the linear one, than the one achieved by this optimal linear contract. Okay, so what should we take away from these theorems? Well, one thing is that in this particular case, the worst case regret is pretty high, if the number of experts is large, especially. And in general, these scoring rules these optimal scoring rules don't do particularly well, because they give such a large fraction of the profit away to the experts. So especially if the experts, in fact, don't pay much for the information that they obtain, then this scoring rule is in practice doesn't do particularly well. So one big driver of this result is that the principal only scores based on the aggregate report and doesn't, for example, try to figure out which expert contributed how much, or doesn't ask the experts about how big one another's contributions were. And these things are quite complicated to do, and in many cases not practical. But given that the regret bound is so bad, we might imagine that in practice, the principal really should do something like this, or should do other stuff to avoid this worst case regret approach. In this particular setting, where all available evidence is all possible configurations of available evidence are possible. The more interesting conclusion, I think, from these theorems is that linear contracts are the optimal contracts in this setting. And there's a long history of papers in economics, mainly on principal agent problems and principal expert problems, which show that under various conditions, linear contracts are optimal. And we now have another setting with multiple experts, which most papers don't consider, where linear contracts are also optimal. So in the paper, we have a couple of more results, including some cases where the regret bounds aren't as bad, and also in the single expert case, of course, the regret bound isn't that bad, and in these other cases too, the optimal contracts are linear. Okay, so if you're interested in linear contracts and then principal agent problems or principal expert problems, then you might find the full paper interesting. And thank you for watching this presentation.